Hello, my name is William Margelis. I'm being joined by Olivia Lindley and Gabriel Thornton. We are doing a Physics 211 group project number 2. Go ahead. So for the problem we chose for today, we are looking at two boxes of different weights. You have the blue blocks and the red blocks are both sitting on a frictionless level surface. And at the end of the tables, the box at the left end of the table, the box with weight MB is compressing a spring with constant K at distance X initial. Starting from a resting position, the box moves forward to the right until it collides with the red box on the other side. The boxes collide and stick together and continue moving towards the right, colliding with an identical spring identical to the first. So what we know and what we are assuming. So for in this problem, our constants are going to be K, the blue block, and the red block. K is our spring constant, and then the mass of the blue block and the mass of the red block. What we know this is going to be an elastic collision. We know that the change in kinetic energy, or excuse me, change in kinetic energy is 0, and then the change in potential energy is also going to be 0. So the box with weight, the red box, excuse me, is initially at rest. So our assumptions and also what we know, the table is frictionless. Moving in the right direction is for our problem is the positive direction. If the springs are identical, the spring constant are also the same among the two springs. And in our system, there's no external forces acting on the system. Yeah. And then the red block has a larger initial mass than the blue block. So in our diagram, like the systems in use is going to be energy, force, collision, and momentum. As we said earlier, going to the right is in the positive X and going to the left is the negative X. Up is Y, excuse me, and then down is Y. But in this problem, we are just going to be mainly looking in the X axis. So initially, the blue block is compressing the spring at X initial. And then you can see the spring shoots the blue block into the red block, causing them to collide. And then finally, they stay connected and then go all the way across the table, compressing the spring on the right-hand side. And in our force diagram, you can see force and gravity are the normal force and gravity are canceling each other out. And then there's no friction. The only thing that's being pushed on to the blue block is the red block itself, but it's still pushing forward from the spring force into the other spring. So some of the concepts and like definitions that we use in this problem. So energy of a system is a physical property measuring its ability to exert a force that can impact the displacement of the other system. And we also are looking at momentum, is the mass of the object times its velocity. We are also using Hooke's law, which is spring force equals negative spring constant times its distance. And then elastic energy, 1/2 spring force times its change in X squared. We are also looking at kinetic energy, 1/2 mass times velocity squared, as well as potential energy, which is mass times velocity.
Awesome. Thank you, Kainoa. So starting off, as you mentioned earlier, we have our two ways of going forward, either energy or momentum, and we will be starting with kinetic energy and elastic energy in our formulas. So we have 1/2 kx squared equals 1/2 our mass of mb vi squared mb. And then you can assume at this point that the mb masses are combined. This is one mass. So we divide by 1/2, eliminating the 1/2, and we go to kx squared, which is our spring constant, and then the change in x squared equals our mass of the red block times vi squared. And now we need to get vi alone, and not only squared, but as a square root. So we divide by mb, take the square root of kx squared, is over mb, equals vi. And this represents Hooke's law and spring force, the elastic energy, which is, as I mentioned, 1/2, and then the change in x squared with our spring constant as well. And then the initial velocity in the equation solved will give us our missing variable to solve for the velocity final, which now we are switching over to momentum equations. Awesome. So as I stated, you can now use momentum. We have the mass of the red block times velocity initial equals the combined masses. This is our second collision of MB plus MR times V final. And so we have MB times the square root of KX squared over MB. And this is the VI we just solved for previously in the slide, equals our combined masses times our velocity final. This once again reflects that mass times velocity equals momentum. So now we know we need to get our V final alone. So how do we do this? We take our combined masses and divide it by MB times the square root of KX squared over MB. And once again, our KX squared over MB is our velocity initial in the previous equation back when we were using energy. Awesome. So further into our solution, we can now substitute final velocity back into our equation, which we just found. So we have 1/2 our combined masses again, because we're looking at the second collision as the spring is going to compress, times MB, square root of our spring constant, distance squared, over MB again, over the combined masses, and all of this squared equals 1/2 KX squared. So to make things easier on yourself, you should have 3 sets of total masses, and you can eliminate 2 just by cross multiplying. So you eliminate MB plus MR over MB plus MR, and you're left with 1 MB plus MR times MB KIX squared equals 1/2 XF final. Now, super easy. You divide your 1/2, like I mentioned earlier, and you get a value of 1. You now have XF squared equals MB times KXI squared over MB plus MR. And we take the square root of both of these to get XF just by itself and not squared. We need a singular value because this is our total distance change. We now have MB times KXI squared over our total mass equals our final distance. And as the problem mentioned, we know our springs are the same. If you divide same values that are the same, you should end up with 1. So 10 divided by 10 is 1, and our spring constant divided by spring constant, if they're equal, should give us a value of 1. So this is dismissible in our equation, and we are left with MB over another mass, and then our meters.
I will be going over the unit to verify that they are correct. And so as we can see with our equation that gives us our final answer, the square root of MB times K times the initial X value squared divided by MB plus MR equals our final distance. So we know that MB and MR are our masses. They should be in kilograms. And distance should be for our initial distance is in meters. K is a unitless number because it is our spring constant. And so in our equation, it is irrelevant. We can throw it out. And so we are left with mass times distance squared divided by mass plus mass. And so the two masses underneath are combined to just mass, and then the mass above and below are canceled out. And so you are left with the square root of the distance squared, which just equals our distance. So we are able to find out that our units are correct because we are able to verify that through plugging in our units, that we are able to find that distance equals distance. And so we do this by dividing both spring constants by each other. And if they're the same value, because they're identical, we can eliminate it. And we also know that the 1/2 value, which is if set to itself, can also be eliminated through division, which means we are still left with mass over mass, which eliminates itself through the square root and the initial squared, which leaves us with our distance in meters. And so what happens if we change our variables? Well, if we add friction to it, such as changing our system, we have to account for the deceleration of the boxes. And so our system is currently the 2 boxes, the table, and the earth. We do this and so we can ignore friction, even though our table is frictionless, and we can ignore the force of gravity. But if we just make our system the 2 boxes, then we have to account for friction and gravity, which we don't want to do. Or what happens if we change the masses of the boxes? Well, if we, for example, change the mass of block MR, which is the block that is initially at rest, to a smaller value, we will see that the two boxes after the collision will not stay attached to one another. It won't be an elastic collision after they hit, which is why we are assuming that blocks MR is initially a larger mass. We also found that if they are the same mass, they also will not cause an elastic collision because there won't be enough force to push MR forward. And so what happens if we change the spring constant of either or both springs? Well, the reason why our equation and final answer works is because the two springs are exactly identical, which means that their spring constants are also identical to one another. And so if we make one of them greater than one of the other, then we have to solve for each constant separately and not eliminate them having equal value. And for our reflection, we found that this problem was very similar to our energy and collision lecture problem that we did during class. Both projects revolved around an object moving towards another that is at rest and colliding with one another. Though in our lecture problem, these two objects had different masses and was not an elastic problem like the one that we solved. It also did not involve springs, while our problem that we did here did. We also found that it was similar to homework 9, colliding astronauts, where again, they both centered around an object moving towards another object and colliding with it. But the main difference is that problem that we did for the homework revolved around finding the ending velocity of the second object that was collided with, rather than finding the distance of the spring compression. So that is all for our presentation. We thank you for listening, and we hope that you have a good day.